Hi, my name is Jim, and the topic today are Norton equivalent circuits. This will serve as a good lead-in for nodal analysis, and what it's about is transforming a voltage source into a current source and a current source into a voltage source. So you might ask yourself what current sources are about. Everybody has a pretty good idea what voltage sources are. We buy batteries most certainly, and that's a good example of a voltage source. And do note that all voltage sources have an internal resistance. It may be quite low and hence not enter into calculations, but every real voltage source has an internal resistance. Now with regard to a current source, about the only thing that I know of that has characteristics that resemble one are solar cells. But perhaps more importantly, it allows us to model things and solve calculations much easier than if we were just to use voltage sources. So the question is how do we convert back and forth between the two of them? Now, speaking about modeling, here we have the diagram of the collector characteristics of a transistor. And though it's well out of our topic area right now, what this stands for is the voltage from the collector to emitter, and this stands for the current in the collector. And what I want you to pay attention to is the flatness of these curves. So as M approaches zero, this looks more and more like a current source in the model of a transistor, not only a bipolar transistor but field effect transistors, and it makes the analysis very straightforward. So although a transistor does not create current, and what it truly is a current sink, but in the model of it we just call it a current source. So the symbol for a current source is a circle with an arrow through it that points in the direction of conventional current, and it also has an internal resistance. A perfect voltage source has an internal resistance of 0 ohms. A perfect current source has an internal resistance of infinity. So they're very much opposite. Now let's take a look at the external circuit, which would be connected out here on a voltage source. And if we look into this, is what we would see would be our internal, because this component of a voltage source has a 0 ohm internal resistance. So if we looked in here, effectively what we would see would be our internal, and that's it. Contrarily, with a current source, if we remove the load and looked into it, what we would be doing is removing the current source, and what I'm doing is opening a lead here. So again, what we're going to be seeing is our internal. So it's very important that you know this, is that the internal resistance of a perfect voltage source is 0, and the internal resistance of a perfect current source is 0. In practicality, it's going to be our internal. This one's going to be in series, this one's going to be in parallel with whatever loads we elect to connect to it. So how do we convert to a current source? And I'm using an example here with 12 volts with 24 ohms that I'm calling our internal. And the way we would do that would be simply short the output of the supply. Now, this is a very bad idea to do with a real voltage source. That can lead to some real problems. But mathematically it's perfectly fine to do it, and then all we would do would be finding what I'm going to call the short circuit current, and the only thing that's limiting this current is the internal resistance. So in this case I've got the current equal to 12 volts divided by 24 ohms rather, and that gives us a current flow of 0.5 amperes. Once we have that, all we have to do is assign that to a current source, have the arrow pointing in the same direction, and then use exactly the same internal resistance in the current source, only we place it across the current source. So next let's convert from a current source to a voltage source, and the way we do that is we remove the load again, and this current source is 0.5 amperes, and all of that current is going to be flowing through its internal resistance, and that's going to produce 12 volts. And once we know what that voltage is, all we have to do is take our internal resistance and then put it in series with the load, and we're finished. So that's kind of a quick overview of voltage sources and current sources. It'll be very useful in up-and-coming nodal analysis, for example, to do the transformations, and you should be comfortable with it, even if it's fairly abstract. So that'll conclude, and thank you for watching.